The average rate of change of a function over an interval is one way to measure how fast a function is increasing or decreasing. It is a commonly computed value and has important implications in calculus. Let's start with the general notion of rate of change. In general, a rate of change describes or measures how an output quantity changes relative to the change in an input quantity. The units on a rate of change are output units per input units. Let's consider some really basic examples. A population increasing by 1,200 individuals per year, or a car traveling 65 miles per hour. We could consider a car traveling 28 miles per gallon. So in example 2, at 65 miles per hour, we're talking about a speed, a rate of change in mileage relative to time. And in example 3, we're talking about a fuel economy, a rate of change of mileage relative to gallons of gasoline used. We could be considering the amount of money in a savings account increasing by $50 per month, or maybe a temperature drop of 3 degrees per hour. Now let's consider the average rate of change of a function. The average rate of change of a function, f, over a closed interval from a to b, is given by the change in output divided by the change in input. We often use an uppercase Greek delta to denote change. So delta y represents a change in y, and delta x represents a change in x. Since y values are function values, the change in y is the ending function value minus the beginning function value. Also, the change in x is the ending input value minus the beginning input value. Thus, the average rate of change of a function f over the closed interval from a to b is given by the quantity f of b minus f of a divided by the quantity b minus a. Note that the average rate of change of a function f over a closed interval from a to b is the slope of the line through the points b, f of b and a, f of a. Let's look at a diagram for additional clarification. We are given a graph of a function y equal f of x over the closed interval from a to b. If we consider the line through the points b, f of b and a, f of a, we see that the rise is f of b minus f of a, and the run is b minus a. Thus, the change in y over the change in x, or the average rate of change, is exactly the slope of this line. Now let's consider an example problem. We want to find the average rate of change for the function f of x equal x squared on several closed intervals. I almost always start my solutions with a sketch or graph of the function involved. Even though a graph isn't strictly necessary, producing one helps get my mind focused on the problem. This also prevents me from staring at a blank page and not knowing what to write to start the problem. Let's add points on the graph that correspond to the endpoints of the 3 closed intervals. Notice that the function values are easy to read from the coordinates of these points. Now, on the closed interval from -2 to 0, the average rate of change is the change in function values over the change in inputs. Notice we've used delta f in place of delta y. These notations are often interchanged. We get that the average rate of change on the closed interval from -2 to 0 is -2. On the interval from 0 to 1, we get f of 1 minus f of 0 over 1 minus 0. Since f of 1 is 1 and f of 0 is 0, this fraction, or rate of change, reduces to 1. Finally, on the interval from 1 to 2, we get that the average rate of change in the function is 3. The average rate of change of a function over a closed interval is closely related to the concept of different quotients, which is what we will discuss in the next video.